microphone. Okay, so we will continue with Ben Hoare from ETH Zurich with a talk. Well,
right, there we go. Sorry about that.
Okay, with a talk about sigma models with local couplings and the new connection between integrability and RG flows.
Great, thank you very much for the introduction, and I'd like to start by thanking the organizers for giving me the opportunity to present this this work here today. What I would like to talk about today is a new connection that we've found between integrability and RG flow, and this has led us to investigate sigma models with local couplings. And this is based on this paper down here, written with Nat Levine, who is finishing his PhD at the moment at Imperial College, and Arkady Zelin, who I guess most, if not all of you, know. Okay, so let me start. So what I wanted to do is first motivate what I'm going to talk about today by discussing two observations. The first one is a remarkable link between classical integrability of two-dimensional sigma models and their stability under renormalization group flow, at least at one loop. And this idea has been around, the origins of this idea has been around quite a long time, since the early 90s, when integrable deformations of some simple sigma models were constructed by looking for solutions to RG equations. So there's a simple, one of the simplest cases here is a picture. So we have a sphere, two sphere. So here I'm thinking this is the target space of the sigma model. And then as we deform this two sphere, we can also understand this as deforming the sigma model itself. And in terms of embedding coordinates, so this is just x1 squared plus x2 squared plus x3 squared is 1. And we just introduce, at leading order in the deformation parameter, we just introduce a factor here. Eta is the deformation parameter. And then there's a whole higher tower of corrections that are needed actually for this thing to solve the RG equations. So it was understood actually quite a lot later that this model is actually integrable. So by solving the RG equations, you actually find an integrable deformation. And I think probably the most modern or most precise way of formulating this idea is that it's sort of believed that one-loop RG trajectories, if you follow a one-loop RG trajectory, you stay within the class of classically integrable sigma models. This has been checked on many examples by now. So these include examples where the global symmetry essentially does this for you. It constrains the RG flow to stay within the same class of models. And this includes, for example, the principal chiral model. But it's also been checked for models such as these integrable deformations I mentioned on the previous slide, for which renormalizability at one loop is actually non-trivial, with only finitely many couplings running. Let me just also mention two related developments. This can be extended to higher loops, and it also underlies a duality with integrable massive models. So I think the ideas on this slide, there's been a lot of activity discussing it in recent years. I didn't really have space to kind of list all the citations. You can find them in the paper. But there's a sort of underlying question for this, which is how does the classical integrability translate into simple quantum behavior? So that's the first observation that we'll come back to in a second. But first, let me move to the second observation. And this is that there's an interesting class of string sigma models. And these string sigma models have backgrounds of the form I've written here. So they have metric and dilaton switched on. The metric has the following form. So it's du dv plus some transverse metric, depending on coordinates xi. And this transverse metric can be curved. It can be a function of both x and u, but it shouldn't be a function of v. And the dilaton should be linear in v plus some function of x and u. This metric admits a covariantly constant null killing vector, which just corresponds to shifts in v. And the dilaton, as I said, is linear in this coordinate v. So what's interesting about these models is that if you, well, here I've just written the classical worldsheet Lagrangian and conformal gauge. And if we consider this model on a general two-dimensional worldsheet and ask when is it Wahl invariant, So when does it describe for us a string sigma model, at least if we're in critical dimension? Val invariance at one loop implies that this transverse sigma model should solve the RG equations where u, this coordinate u, is now formally playing the role of RG time. So that's some words in equations. We have the following relation. So on the left-hand side, this is the Val invariance conditions for this first sigma model on a curved worldsheet. And if you just plug in this ansatz for the background into this equation, what you'll find is that these equations are solved if this transverse metric solves this first order equation. So du of g is proportional to the Ricci tensor plus some dilaton term. And this is essentially the one loop RG equations for this sigma model here. So we can go a bit further. We can try to fix the residual gauge symmetry. So in conformal gauge, the equation of motion for V is very simple. It just solves the free, it implies that U solves the free wave equation. And we can fix the residual gauge symmetry by using light cone gauge. And we just set U is equal to tau. So already we see some interesting relationship here, which is that the RG time, I'm relating somehow the RG time to the real time tau. And what we're left with is a time-dependent theory for the transverse coordinates xi. So this is the light cone gauge fixing of this model here. Now, this motivates us to, this is the question that I want to try to answer in this talk. And this is in part motivated by the goal of finding new solvable string sigma models. We're led to the following question. So if we now take a sigma model that's classically integrable and is renormalizable at one loop with only a finite number of couplings HA running, then this sigma model, using the construction I just described, can be embedded into a Val invariant sigma model where now these couplings depend on the coordinate u, and this dependence is determined by the one loop RG flow. So this is that sigma model written here. And then the question we want to try to ask is the light cone gauge fixed theory, so now we just replace u by tau, is this classically integrable? So this is essentially, can be this final Lagrangian can be thought of as the same sigma model that we started with, but where now the couplings are local couplings, they depend on the worldsheet coordinates. Okay, so that's my introduction. That's the question that I want to try and answer today. The outline of the talk is as follows. So most of the talk will be on constructing lax connections for these models. That's the main result of this work. If I have time, I'll say something about conserved charges, and then a brief comment on what happens for massive models, and then I'll conclude. Okay, let me turn to lax connections. So as a working example, I'm going to consider the principal chiral model, which I think we all know very well, for the simple Lie group G. So what is the principal chiral model? It's just a 2D sigma model whose target space is the Lie group G with the round metric, And just to set some notation, here d plus d minus are just light cone derivatives on the worldsheet, d tau plus minus d sigma, tau and sigma are space and time. G is a G-valued field, and G inverse dg pullbacks to the Mara-Cartan-1 form. Minus the trace is a positive definite ad invariant bundling form, blah, blah, blah. And this model has a GL times GR symmetry. And given what I'm talking about today, probably the most important thing is just to point out this H. So H is the sigma model coupling, and it's proportional to the radius squared of the space. Okay. So this model has the two properties that we want. So the first thing is that it's integrable, and in particular, what I want to focus on is that its equations of motion are encoded in the zero curvature of this lax connection. So you take this lax connection, you compute the zero curvature, you demand that it vanishes for all z, so z here is the constant spectral parameter, and you'll recover the equations of motion of the principal chiral model. The model is also renormalizable at one loop, and only, well, there are no new couplings introduced, so only the coupling H runs. And it runs in the following way. So here dh by dt, so here t is the RG time, is equal to c, where c is the Joule-Coxeter number of g. And so we solve this easy, h is linear in the RG time. And it's basically, we can rescale t to eliminate c. So from now on, I'll basically set c equals 1. This is just for simplicity. It can always be reintroduced by rescaling the relevant variable. So using the construction that I described in the introduction, we can use this to construct a conformal gauge string sigma model in the following way. So we have the du dv term, and then we have essentially the principal chiral model, but now with h replaced by u. So what was the logic before? We start from the model, we replace h by its solution to the one loop RG equations, and then we replace the RG time by this coordinate u. So that's exactly what we have here. And the Lightcomb gauge fixing of this then just amounts to setting u equals tau. So we've got what we thought we got the PCM with a time-dependent local coupling. And the question rephrased now for this model is this model classically integrable? So what we're going to try and do is construct a lax connection. So I've rewritten the model here. If we write the equations of motion in first order form, so I'm going to introduce J as just these G inverse dG, then the first equation is basically the conservation of one of the Noether currents associated to one of the G symmetries. So here tau times J is essentially the Noether current. And the second equation is just encoding that J is G inverse to G. So just the zero curvature of J. And we're going to assume the following ansatz for the lax connection. So it's basically the same as before, except now that Z will depend on W. W is going to be our new spectral parameter, so the new constant spectral parameter, and Z is also allowed to depend on tau and sigma. So this is our ansatz, and what we find is that if Z takes the following form, so square root of this expression based on W sigma tau, then we can compute the curvature of L, and we find two terms which are proportional to different functions of Z. And the first term is proportional indeed to the equation of motion, and the second one to the zero curvature of J. So demanding that this vanishes for all W indeed implies for us the equations of motion. So this lax connection has a number of unusual features, kind of interesting features. So Z, firstly by almost construction, Z is now a function of tau and sigma, while W is our constant spectral parameter. The sigma model we started with only depended on tau. The coupling, we chose the coupling tau, coupling H to be replaced essentially just by tau. However, what we find is that the lax connection depends explicitly on the spatial coordinate sigma, and that seems to be a necessary feature. There's also this observation that W, so the spectral parameter and the spatial coordinate sigma, they always come in this combination W plus sigma, and we have some understanding of why this happens from a technical point of view. However, it feels like there should be some deeper understanding of what's going on here. And finally, we note that this lax connection seems to also necessarily have some complicated analytic properties, including that there are sort of position-dependent branch cuts in the W plane, which don't be so easy to get rid of. So what we've done so far is that we've established that when the local coupling is determined by the one-loop RG flow, we can construct a lax connection. But it would also be nice to have a converse statement. So for which local couplings can we construct a lax connection? And is the local coupling that comes from the RG flow, is that special in some sense? So to do this, we just consider the PCM with a generic local coupling. So I'm just going to replace H by some function of tau and sigma. The equations of motion are just written here. So it's basically the same as before, except that tau is now replaced by H of tau sigma. We again assume the same ansatz. This ansatz can actually be relaxed a bit, but for purposes of this talk, I'm just going to assume this ansatz here. So the lax connection takes exactly the same form as before, but now Z is a function of W, tau, and sigma. And if we compute the corresponding curvature and rearrange the terms in this particular way, we see the final term here is basically the zero curvature of J, and then the remaining terms should vanish on the equations of motion. So by comparing the different structures, you can get a series of equations. And what you find is essentially that the lax connection exists if this function h is equal to a function of xi plus a function of xi minus, where xi plus and xi minus are just like cone coordinates on the world sheet. So if these f plus minus are equal to xi plus and minus, then we just recover the original time-dependent case that we discussed originally. And then we just notice that this freedom that appears, this apparent freedom that we have is actually just completely expected, because it just corresponds to 2D conformal transformations of the time-dependent case we had before, and these transformations preserve the form of the Lagrangian. And it can also be understood from the conformal gauge string sigma model point of view, where ignoring boundary conditions to fix the residual gauge symmetry, we can just take U to be any solution of the free wave equation. So what's the message here? The existence of a lax connection implies that the local coupling is determined by the one-loop RG flow up to conformal transformations. So let me just mention very briefly, there are some interesting special cases. So if f plus f minus is a constant, we just get the PCM. As a kind of halfway house, you could consider f minus as a constant, and then you get what we call the chiral model. It's probably not the best name because, I don't know, chiral principal chiral model. But it's invariant under half of the conformal transformations. And then if you go all the way and pick something like f plus f minus is tau, then you have not, you don't have so much symmetry left over. So one may think that, okay, PCM is a very special model. Is this all accidental? I think it's important to highlight that it's certainly not accidental. This whole construction can be generalized to a number of other sigma models. I think we tested it on 6 different cases of varying degrees of complexity. So the first one, which is maybe a straightforward generalization of the PCM, is the symmetric space sigma model. You can also add a Wess-Zumino term to the principal chiral model, breaking parity invariance. The construction still works. And then various deformations. So the Q deformation of the principal chiral model, which is often known as the eta deformation, it generalizes the squash 3-sphere of Sharednik, and it's what's interesting in particular is it's a 2-coupling model. And then also the isotropic current deformation of Wess-Zumino-Witter model, known as the lambda deformation, and an analogous deformation of the gauge Wess-Zumino-Witter model. And what's interesting about this final case is that the sigma model has no global symmetries. So for many of these, the RG flow is much more complicated, and the existence of a lax connection is rather non-trivial. So as an example, I just want to briefly flash some results for the Q deformation of the PCM, just to highlight this. So what is the Q deformation of the PCM? This is the action. We just insert some linear operator in the PCM between the two currents. And here R is a linear operator. It annihilates the Cartan generators of the algebra, and it acts on the roots in this way. And this is a 2-coupling model. There's H, which is the radius squared, and the deformation parameter eta. And well, this model has the 2 properties we want. It's integrable. The lax connection is written here. It's also renormalizable at 1 loop with the couplings eta and H running. These are the equations. These are the solutions. Nu is basically an RG invariant, and then the expression for eta is given implicitly by this second equation here. So what we can do is we can use these functions that solve these equations, these one-loop RG flow equations, when we construct the time-dependent model in the same way as before. And we find this again admits a lax connection of the same form as the original model, with basically these replacements. So eta and H are replaced by their time-dependent counterparts. And then the spectral parameter, or this Z, which is a function of the spectral parameter W, is implicitly determined by this equation here. So again, the existence of the lax connection also implies that the local couplings are determined by the one-loop RG flow up to conformal transformations. Okay, so let me just summarize what this main result is. So if you take a classically integrable sigma model and you let its couplings be time-dependent functions, and then those time-dependent functions are essentially determined by the one-loop RG flow of your original model, then you can construct a lax connection in the time-dependent theory. And we've tested this on a number of integrable two-dimensional sigma models. And this establishes a new connection between classical integrability and RG flow, which I think is...
You have 5 minutes left.
Okay, thank you. Okay, let me just very briefly say a couple of words about conserved charges. So going back to the simplest example that we have, the time-dependent PCM on 2D Minkowski space, we can choose, I'm going to choose this particular branch of the lax connection. And this is because if you take sigma to plus or minus infinity, then Z goes to -1, and the lax connection vanishes, assuming that J plus or minus are bounded. And this means that the monodromy matrix is conserved. Yeah, so we're on 2D Minkowski space here. However, what's kind of interesting is if you try to expand the monodromy about W is minus infinity, you get sensible expressions. So leading order, you just get the identity. Then at first order, you get the Noether current associated to the G symmetry. And then you get some generalizations of the multi-local Yangian charges. However, what you notice is that you start to get this sigma dependence. And that means for term-by-term convergence in this expansion, we require increasingly strong decaying boundary conditions on J plus J minus. Things get a bit more complicated when we're on a cylinder, so I'll leave that for the moment. And let me just briefly mention something about massive models. So I think this is quite important. So the construction also works for the Sine-Gordon model. So if you replace the couplings G and the mass M by functions of tau, where these functions are basically specified by the one-loop RG equations, then this resulting time-dependent model appears indeed to be integrable. And actually, the relation is much simpler in this case compared to the simple models, sigma models, because this time dependence can be eliminated just by doing a conformal transformation. So this is strongly suggestive that these massive models may help to give a better understanding into this relationship between the integrability of these models with local couplings. So let me just turn to my conclusions. So, well, let me repeat the main results. So we've established this new rather surprising connection between classical integrability and RG flow. If you take a classically integrable sigma model, promote its couplings to be time dependent, then you can generalize the lax connection if these couplings are determined by the one-loop RG flow. And the lax connections we found had a number of unusual features. They depend on both tau and sigma, and they have a more complicated analytic structure than is usual. And it gives rise to a classical origin of quantum RG flow. So I think there are many open questions to be answered about these models. So first is a general proof of the relationship possible. I think this is always a nice question. Thinking right back to the beginning of the talk, one of my motivations was to find solvable string theories. Can this construction be used to actually solve the string sigma models and compute the spectrum or something? Would be very interesting. What is the underlying algebraic structure? Can that be used to help understand the extent to which integrability is actually present, is useful in these models? Can we understand these theories at a quantum level? I think is also an interesting question. And then finally, I mentioned a few times in the talk that somehow, well, W appeared in combination with sigma, and this combination W plus sigma, and there were some other things. But somehow W, sigma, and tau look like they're appearing on the same footing. And that's rather suggestive. We saw a very nice talk by Bogdan earlier today. It's rather suggestive of these 4D Chern-Simons theories, where somehow, again, the spectral parameter and tau and sigma at least put on a more similar footing than is usually the case. So the question would be, is there an origin from 4D Chern-Simons? And with that, I would like to say thank you for listening. And seeing as the final discussion session is hosted by Pedro, before I hand back to Didina, let me just say a big thank you to everyone involved in organizing the conference. I think this has been well, somewhat exceptional, but very, very successful IGST. And yeah, so thank you very much from all the participants.
Thank you, Ben, for this nice talk. And also thank you for, I wanted also to thank the organizers for this creative and exceptional edition of IGST. So, let's go to questions before switching to discussions. So, questions. Volodya.
Ben, and if you try just blindly insert into your formulas that the second loop of principal chiral field, all this magic will fail because you have only these two loops are universal. Yes, it's natural to try two loops.
Two loops. That's a good.
It's a trivial coefficient, yes, 1/2 log mu in principle.
I think I thought that, well, so you're testing my memory. So the running it, I thought that for the PCM, the two loop correction is basically just this C gets corrected to something like C plus C squared over 2. So H will still be linear in T.
No, you have
no. There is one over H.
You have two loops.
Expansion in H.
Yes, sorry. Yes, okay. No, then we did not look at this.
No, but the whole point is this is purely classical on integrability side. So you just have asked about classical.
So
yeah, so it's kind of classical quantum. So if we push these two loops in RG, we will need to correct lux by one of the coupling terms. So
yeah,
like H bar terms. Yes, that would be interesting to see if that can be done, but it's.
But with this ansatz for the lax, the coupling needs to be linear in time. So it won't work if you put the two loop solution.
So you simply say that it will fail. For sure.
Well, I think okay. So then
you'll need to.
Maybe I can just add. I think this idea that Arkady said of how to correct the lax is something that is not understood. I don't think there's any ideas of how you do this. So, I mean, first you would have to understand how what it means to correct the lax connection by order 1 over h bar corrections, and then if you could understand that, then you may expect that two loops on the RG flow corresponds to somehow a one loop correction to the lax. That would be the idea, but I think there's probably quite a few steps.
Sorry, but maybe just a related question to what Vladimir asked. Like in this massive sector you demonstrated, when suppose I'm replacing those characteristic parameters like in Singardon of the coupling and mass by the tau functions, this is universal. So you say in this case, this automatically implies that I'm satisfying one loop RG flow equations. But maybe this is for if you yeah, this is just an example. I mean, so this works this way, just one way, and probably I'm not sure how would be the argument the other way around. For example, you find some RG flow equation which you satisfy. Would they satisfy some, or could you identify what kind of integrable models they would satisfy? This is maybe first question. The second question, can you pose, like if you go to higher loop RG flow equation, like what Vladimir tried to address is, maybe you can constrain the lax deformation such that the corresponding correction satisfies the given RG flow system.
Yeah, that would be an interesting. Yeah, the second question certainly would be a very interesting way of exploring corrections to the lax connection.
To pose the deformation in such a way that it is satisfied, maybe by constraining it by some extra relations. Like I think by extra relations, I mean maybe this is exactly related to what you mean by underlying algebraic structure. So you if it is possible to find some closed relations on the same universal tau functions or something like that.
Yeah, I mean, I don't think I have anything particularly concrete to say, but I think that these are very interesting comments. Yeah.
So, Alessandro.
Maybe I can ask, did you try to compute the Poisson brackets and see whether there's any R matrix, classical R matrix controlling them?
We did. I think it's a bit related to these local charges and this story. So what you find is that there is indeed a classical R matrix that now depends on sigma or tau or both explicitly. But this R matrix, so let me say some words for those of you who know what there is this idea that if the R matrix is of what's often referred to as twist form, then you can use this to construct these local charges. So what we find is that there is an R matrix. This R matrix is not obviously of twist form. And then there seems to be some issues with when you try to construct these local charges, how this goes through. But I think there's probably some steps that we're moving a bit too fast through, and one should look more carefully at this analysis. But the first part, that there is an R matrix, is definitely the case.
Okay, thank you.
So Sergey?
Hi guys. I have a very naive question. Your spectral parameter depends only on sigma plus W, right?
Mm-hmm.
Why can't you just shift sigma and get rid of W?
It's an interesting question. I mean, shift sigma. So, I mean, W is in principle meant to be a very simplistic answer is that sigma is real and W is complex.
Well, you don't know it, yeah? W just something.
A more complicated answer is that I think it's a very interesting question. It's kind of, I don't know whether Nat or Arkady have something extra to say, but I think it's something that is, as I say, I think there should be some deeper structure behind this kind of dependence on W plus sigma. There should be some meaning to it, but I don't think we fully understand.
I mean, if you shift sigma, then you don't have any W and you don't have really Lax pair, which depends on the parameter.
Sure. Well, yeah, I mean, you would get some more, you would basically somehow say that all of this equation is just one big equation.
Right.
And that's the equation that you get.
But I would say W is complex, and it doesn't necessarily make sense to.
Well, we don't really know that. Yeah, at the moment it's all algebraic. You can say that sigma is complex too.
Look, I think it's an interesting point. I don't think we fully understand it. I mean, certainly if there were to be some origin from 4D Chern-Simons, then sigma would be real and W would be complex, and that would be that. And so I think there's some meaning to this relation, but I don't know what it is. But it's certainly not trivial that these things work out in this way.
But maybe just the point that J plus minus doesn't depend on W.
Yeah, that's a good point. Yeah. Wow. Yeah. Okay. Yeah. That's an interesting point. Yeah. So
I actually have one more question. Well, in principle, if you can see the curved background, like ADS2,
Okay.
yeah, then you also have a time dependence. So, well, dependence on sigma tau, depending how you consider it. Is it covered by these models?
Can you just say which model do you mean?
I mean, if you consider the sigma model on ADS2.
No, I don't. I think so. Yeah, we have added we will add a comment in a second version. So basically that's saying if you can this time dependence be incorporated into just a metric on the world sheet? Can you reinterpret this in this way, right?
Yeah.
So no, I don't think. I think the answer is no, essentially because these models should be conformally invariant. But sorry, what do I want to say?
Yeah, the answer is no. Yeah, if you consider generic curve background, you can always change coordinates so that sigma model doesn't depend on the conformal effect. While this model does depend on a function of tau. Whatever change your coordinates can do.
I see. Okay, thanks.
Good. So let's take a question from Tristan.
Yeah, in some ways it's maybe related. So if you take 4D gravity and you dimensionally reduce it to 2 dimensions, you get this integrable gravity, right, by Nikolai.
Oh, sorry, I can't actually. You're very, very quiet. I don't know whether it's just me or.
No, his microphone is very low. Can you speak louder, Tristan?
Yeah,
please.
So, sorry. Yeah, so if you take 4-dimensional gravity and you dimensionally reduce it to 2 dimensions, you get integrable 2-dimensional gravity, right? This was done by Nikolai. And it has a lax operator that looks very similar to yours. It has this coordinate-dependent spectral parameter where you get this square root mixing. It actually looks very similar. So, okay, my question was, is it the same? But from the look on your face?
I don't know. It's very interesting. Yeah, well, thank you for the...
I see, and they also have an R matrix, and they actually even tried to quantize these 2D theories. Okay, yeah. My other question then is, you actually have a much... So there you get like the SU2 principal chiral model, but you have a much more general construction. And then my other question is there some gravity interpretation of what you have? But again...
Okay, yeah. Both very interesting questions. So,
thanks.
Other questions?
I also ask one question.
Yeah.
So it's a basic question. So when the time goes to minus or plus infinity, the couplings go to constants, right? That these Lagrangians that you promote to time dependent, they go to constant values. Again, the constants when tau goes to minus or plus infinity, right?
So, which one are you talking about? The PCM?
All of them, because they are an RG flow, right? So I would imagine that they would interpolate between 2 constant values, at minus and plus infinity.
Well, I mean, PCM. Well, no, yeah. So depends what you mean by plus or minus infinity. So I mean, normally the t is going from 0. Well, it depends on how you t goes from 0 to minus infinity. And I mean, for the PCM, it goes from infinity to 0. So I mean, yes, these are constants, but I mean, PCM doesn't flow between 2 CFTs in that precisely that way, right? I mean,
it's just as simply you just have 0 or infinity.
But there are in this class of models there will be. I mean, so. This lambda this lambda deformation, indeed, there is a conformal fixed point in there. And so there may be such examples within this range of models.
Yes, so PCM with the Weser-Miner term.
PCM with Weser-Miner term also, yeah.
Okay.
We have a question from Sylvain Lacroix.
Yeah, maybe a naive question, but I was wondering if maybe it's possible to promote this lax that you have on before conformal, before the light coordination thing, basically.
Yeah, well, I don't know. We tried very hard. We tried quite hard to do that. Not obvious, and I think one of the main obstructions is again this dependence on sigma. So. I mean, if the lax only depended on tau, then it would be very natural to just try to replace tau by u and see what came out. But because you have also this sigma dependence, it's really not clear how this should be done, and yeah, we don't know.
Okay, and maybe in one of these chiral model, when you take dependence on just x plus or x minus? Is it,
Mhm.
is it possible, or?
Interesting question. I don't think, I certainly didn't explicitly try for this model. Maybe it's a better place to have a go at this. I have a feeling it will still be rather difficult. Well, yeah, it's an interesting question. It gives you, it gives you maybe an ansatz to try.
Okay, thanks.
But or a range of ansatz, because this function can be any function of psi plus, so it could be any function of u.
Okay, thanks.
Yeah. Yon Vancha.
Okay, just a very short question. Do you have this correspondence between, for example, lax operator and RG in the case of Poisson sigma models for Hamiltonian algebroids, for example?
I mean, the answer is I don't know. I think all the models that we tried, I listed. So anything that's not on that list, we didn't try. But surely it would be interesting to look at other examples.
Okay. And another short question then: have you considered interactions in these models? For example, like I don't know, potentials of any kind.
So you mean? Maybe you don't mean like this kind of thing.
Yes.
This is. I mean, I think this would be very interesting. So I think there's a whole class of models, massive integral models. So where you add potentials to these sigma models.
Mm-hmm.
I think, is this what you have in mind? So.
Yes, something like that. Yes.
So
all of them are integrable in this.
No, so what we've looked at is just Sine-Gordon. So the main focus of the work was sigma models, and what we just looked at Sine-Gordon to see what happened. And I think it would be interesting to look at all these other. Yes, this is also
okay.
Very interesting.
Okay, thank you.
Are there any other questions? If not, let's thank Ben again. And I will hand over the microphone to Pedro for the list.